Hello. In this work, we present a novel pipeline for monocular depth estimation using visual and inertial cues. Our goal is to develop a monocular-based method that is metrically accurate and can generalize well across environments. We are motivated by applications that require dense metric depth, for instance, scene reconstruction and mapping in robot navigation. The figure here illustrates such an application, where camera and inertial data collected on board a moving robotic vehicle are used to compute sparse metric depth through visual-inertial odometry. This sparse depth then serves as a metric signal for our depth alignment method. Our approach is presented as a three-stage pipeline. The first stage processes input visual and inertial data. This stage is compatible with existing monocular depth estimation models and VIO systems. The second stage performs global depth alignment. The number of points available in the metric sparse depth map may be in the tens or low hundreds. We fit the monocular depth output against these sparse points in a least squares manner. This computes global scale and shift factors that are then used to convert non-metric depth to metric depth. However, global alignment alone is not enough to capture the more localized deviations in metric depth. To address this, we explore how to realign depth more locally at a pixel level. The sparse depth map that we obtain from VIO informs us about per-pixel scaling factors at specific sparse locations. We can interpolate between these factors to construct a dense scale map scaffolding. This scaffolding serves as our initial guess for rescaling metric depth in a more localized manner. We then formulate local depth alignment as a learning-based task and train our scale map learner network to refine the scale map scaffolding. The network regresses a dense scale map that can be applied element-wise to the globally aligned depth. This realigns depth at individual pixels. Our experiments conclude that local scale alignment helps achieve improved metric depth accuracy. We can see in the example here that the locally aligned depth is more accurate with respect to the ground truth. Using this same example, we can visualize the effect of our approach in 3D space by comparing point clouds reprojected from the aligned depth maps. With global alignment, regions of the scene appear somewhat flat or skewed. Local alignment helps correct these regions, for instance, realigning this book more accurately, pulling the desk surface forward relative to the back panel, and straightening out the center desk leg. When evaluating our method, we use VOID, a real-world visual inertial dataset offered with varying sparse depth densities. Samples shown here use the lowest density setting of 150 sparse depth points. Depth is evaluated in inverse space so as to penalize error at closer depth ranges more than at farther depth ranges. We additionally visualize error maps to highlight where depth alignment is most impactful. Whiter regions in error denote improved metric depth accuracy. In the first sample here, with local alignment, the desk is pulled forward and the wall is pushed back. In the second sample, not only are the steps aligned, but also the handrails on the sides. The third sample is particularly challenging, where local alignment more subtly realigns the flat surface floor and also rectifies the depth gradient at the staircase edge. Quantitatively, local alignment achieves a 30 to 40% reduction in depth error over global alignment only. We observe that a similar reduction is achieved if we train our SML network not on VOID but on a synthetic dataset like TartanAir, with very different environments and simulated sensor settings. This confirms successful synthetic to real zero-shot transfer and highlights the utility of using synthetic training data. Furthermore, if we pre-train on TartanAir and then fine-tune on VOID, we observe even greater depth error reduction. Our evaluation also compares against KBNet, a prior state-of-the-art on the VOID dataset. We expand this comparison by integrating different monocular depth estimators into our pipeline, ranging from META small, that is lightweight and computationally efficient, to DPT Bay at large, a more recent model that is more complex and robust. With all three depth estimators, our pipeline outperforms KBNet. The comparison also shows how our method can leverage ongoing advances in monocular depth models. To investigate generalizability, we test our method on samples from an unseen visual inertial dataset. Even with motion blur and noticeably fewer sparse depth points, our pipeline can still successfully resolve metric scale in dense depth maps. When benchmarking on the Jetson Orin board, our pipeline supports real-time processing. The frame rate varies with the monocular depth estimator that is integrated into the pipeline. To conclude, we show animated 3D visualizations for several samples from the VOID dataset. The prior state-of-the-art KBNet serves as our baseline. Variants of our pipeline with different depth estimators all yield accurate point clouds with respect to the ground truth. The red circles indicate regions where point clouds from our method show particular improvement over KBNet. Evaluation code and models are available at our project repository site. We thank you for your interest in our work.